Now, we've learned a little bit of stuff in collisions, and you realize one thing that was strongly a character of collisions was the fact that on a given particle that was part and parcel of a collision, there was a very large force that the other particle exerted, and for a very short time, for a fleeting period of time, for a very, very negligibly small amount of time. And in that short period of time, what really transpired was it changed the linear momentum of the particle. So essentially, we must give it a certain name. When there is a very large force F, a very large force F, acting for a very short time, let's say there's a particle of mass m, right? And on this, a very large force acted for a very short time dt, let's say. Then Newton's second law tells us that this F is rate of change of linear momentum of the particle. This F is rate of change of linear momentum of the particle, P is the linear momentum of the particle. And this F into dt, which is the impact of a very large force acting for a very short time, was dp. dp was what? dp was change in p. Change in p is change in linear momentum. Is change in linear momentum. And that's the impact. This change in linear momentum is brought about because of force acting for a very short time. And this large force, relatively large compared to other forces in the neighborhood or in the surroundings, this impact of a very large force acting for a short time whose product gives me change of linear momentum is called the impulse of a force. This is the impulse of the force F. And what does the impulse of a force do? Impulse of a force changes the linear momentum of the particle. It changes the linear momentum of the particle, right? That means final linear momentum minus initial linear momentum. This impulse, F into time for which it acts, is given by the symbol J. J, the impulse acting on a particle, is change in linear momentum, which is what? Force into the time for which it acts. Very short period for which this large force acts is called J. And what does it do? The effect of this force is, the effect of the linear impulse is change in linear momentum. And sometimes, we also call it a linear impulse. We also refer to this as a linear impulse, J. A very large force acting for a very short time, the product of that is called a linear impulse, which changes the linear momentum, which is final linear momentum minus initial linear momentum. And very clearly, so this is like a delta P. Delta P means change in P, which is PF, which is the final linear momentum minus the initial linear momentum. There are times where they will tell you, let's say, there is a particle of mass 1 kg. There is an impulse acting on the particle. The particle, prior to application of the impulse, had a velocity, say, I plus j meters per second. After the impulse, let's say its velocity becomes 2I minus 3j meters per second, and they say, what must have been the impulse acting on the particle? That product of the very large force acting for a very short time. What did it do? It changed the linear momentum of the particle. So the linear impulse acting on the particle, the linear impulse acting on the particle of mass 1 kg, it's a particle of mass 1 kg. The linear impulse acting on it would be mass into final velocity, which is final linear momentum, minus mass into initial linear velocity, which is v1. So that's change in linear momentum, which is m is 1 kg, so that makes it simply 1 into v2 minus v1, 1 into v2 minus v1. As you can see, v2 minus v1 is I minus 4j. And very clearly, the unit of linear impulse, as you can see, is Newton into time. So Newton second is the SI unit. Newton second is the SI unit of linear impulse, right? Now, there are times when you would encounter a very simple situation of this kind, where, say, there is a particle of mass 2 kgs, and it's moving along a straight line with a velocity of 5 meters per second, and there is an impulse acting on this. There is an impulse acting on this in the direction of its motion. There is an impulse j. This is the magnitude of the impulse, and let's say it's acting in the direction of the velocity, and which causes the velocity of the particle to become 3 meters per, say 13 meters per second. 13 meters per second. Then the magnitude of the linear impulse. This is linear impulse. Linear impulse in a given direction would be final linear momentum in this direction minus initial linear momentum in the direction of the impulse. The impulse in a given direction, the impulse in a given direction is going to be what? Final linear momentum in that direction minus initial linear momentum in that direction. So this is 2 kg. So final linear momentum in the direction of the impulse is 2 into 13 Newton second minus initial linear momentum, which is 2 into 5. Yes or no? So that makes it 26 minus 10 Newton second. That means 16 Newton second must have been the linear impulse acting on the particle. Suppose there's a particle moving in this direction with a velocity of 4 meters per second, and there is a linear impulse j acting on the particle, let's say mass 1 kg, and there is a linear impulse acting opposite to the velocity, j equal to say 100 Newton second, and I want to find the final velocity of the particle. The particle moving, let's say, in this direction with a velocity of 4 meters per second. There is a linear impulse leftwards acting, which is 100 Newton second. I want to find the final velocity of the particle. Suppose I take random direction. I do not know the direction, let's say, in which the particle would move, but suppose I assume that the final velocity post impulse, just after the impulse is released, let's say the final velocity is v. Then what we need to do is the linear impulse in this direction, j, would be final linear momentum in this direction. See, linear momentum in this direction is mv. Final linear momentum in this direction is mv. So final linear momentum in this direction, in the direction of the impulse. Impulse in this direction, I'll have to take final linear momentum in this direction minus initial linear momentum in this direction. Very clearly, final linear momentum in this direction is going to be minus mv. So final linear momentum minus initial linear momentum in this direction. Initial linear momentum in this direction is going to be minus m into 4. M into 4 is the linear momentum in this direction. So linear momentum in this direction, in the direction of the impulses, minus m into 4. So minus mv minus m into 4, minus m into 4. Final linear momentum in the direction of the impulse minus initial linear momentum in the direction of the impulse. That must be the impulse. So let's do the simple calculation. 100 equal to m is 1 kg. So minus v is this, and then that is 4. That gives us v equal to minus 96 meters per second. That means v equal to minus 96 in this direction is like v must actually be 96 meters per second in this direction. Yes or no? Right? That's how you need to do impulse calculations. Now suppose there is a particle that strikes the earth with a velocity v naught. Very clearly, the earth during collision, it will undergo a collision with earth, which is fixed, right? And as we have learnt in collisions, what would happen is that if e is the coefficient of restitution, the particle will rebound with a velocity ev naught. Very clearly, when the particle hits the earth downwards, the earth will exert on the particle a linear impulse j like this. The particle will exert on the particle, a linear impulse, j like this. Let's say m is the mass of the particle. So then, how do I calculate j? J, the linear impulse between the two, is going to be final linear momentum in the direction, which is m into ev naught, minus initial linear momentum in this direction. In this direction is mv naught, so in this direction is going to be minus mv naught. So minus v naught, right? Final linear momentum in this direction, in the direction of the impulse, minus initial linear momentum in the direction of the impulse is minus mv naught. So that gives me like a e plus 1 into mv naught. Yes or no, right? And you know, impulse is like Newton's third law. So if one particle exerts on another particle a linear impulse j, then it's like the third law. The two particles will exert equal and opposite impulses on each other. So if 30 Newton second is the impulse in one direction exerted by one particle on another particle, then the second particle will exert on the first particle the same linear impulse but in the opposite direction. It's exactly the Newton's third law kind of a thing, right? And just like we can draw free body diagrams for forces, we can draw free body diagrams for impulses, right? Now, let me give you some results. In case of collisions, you know, if there is a particle of mass m1 and there is a particle of mass m2, this moves with a velocity u1, this moves with a velocity u2, and they undergo a collision, inelastic collision, and let's say E is the coefficient of restitution between the two colliding entities. Then, subsequent to collision, let's say this particle acquires a velocity v1, this particle acquires a velocity v2, right? So obviously their linear momenta got redistributed. They exerted equal and opposite forces on each other for a very short time, which was the linear impulse, right? So when they collided, there was a linear impulse that 2 exerted on 1, which would be j this way when they collided, and 1 exerted on 2, an equal and opposite linear impulse of magnitude j. Now, so, you know, we could obtain v1 and v2 given E, v1 and v2. Given E, u1 and u2, we could obtain v1 and v2. How do we do that? Simple. Conserve linear momentum, m1 u1 plus m2 u2. That must be m1 v1 plus m2 v2. That's conservation of linear momentum. And then we can write the expression for E, relative velocity of separation, v2 minus v1 by u1 minus u2, and using these two equations we can solve for v1 and v2. Using these two equations we can solve for v1 and v2, the velocities post collision of the two particles. Now once we know v1 and v2, the impulse, let's say acting on 1, the impulse acting on 1 is going to be m1 into v1 minus u1. The magnitude of the impulse acting on this is going to be this. The magnitude of the impulse acting on this is going to be change in linear momentum of m2, which would be m2 into v2 minus u2. That's the magnitude of the linear impulse that the particles will exert on each other. Now, you know, any one of them we can solve for. For example, I can solve for v1 from these two equations and plug into this, or I can solve for v2 from these two equations and plug into this. Each will give me magnitude of the linear impulse. If we actually solve for v1 and v2 and plug in the values of v1 and v2, then we will end up getting j, the magnitude of the linear impulse, going to be m1 m2 by m1 plus m2 into 1 plus e into initial relative velocity between the two. Initial relative velocity between the two, which is, say, magnitude of u1 minus u2, right? So that's going to be m1 m2. We can very easily obtain this result, m1 plus m2 into 1 plus e. E is the coefficient of restitution between the colliding units, and magnitude of u2 minus u1. Magnitude of u2 minus u1 which is magnitude of the initial relative velocity between the two colliding units. That will give me the magnitude of the impulse. Obviously, you know, this u1 and u2 would, in this expression, would come along with signs. We have to choose one direction positive. For example, if u1 was 3 meters per second like this, and u2 was 5 meters per second like this, then we could have chosen, say, u1 as 3 and u2 as -5, for example, in this expression, to compute the magnitude of the linear impulse between the colliding entities. And mu1 mu2 by m1 m2 by m1 plus m2 is commonly referred to as the reduced mass. Mu is m1 m2 by m1 plus m2 is commonly referred to as the reduced mass of the system. So magnitude of the linear impulse is going to be mu into 1 plus e into magnitude of the initial relative velocity just prior to collision. That will give you the magnitude of the linear impulse between the two particles. Also, you know, there are times when they will give you force time graph, force versus time graph in a one-dimensional situation. And if this is the force time graph in a given situation between time t equal to t1 to time t equal to t2, then the area under the force time graph, in the interval t1 to t2 will give me the impulse. This area will give me the impulse. Now, let me give you another illustration, very fairly simple illustration. So, there's a pulley. There's a particle of mass m here, and there is another particle of mass m here, right? And they're at rest. Initially at rest. There's a small particle of mass, same mass small m, which falls down with and hits this mass m with a velocity u. So there is collision between this m and this m, and that during that period of collision they exert very large forces on each other for a very short time, and therefore there is presence of an impulse that small m exerts on this small m and this small m exerts on this small m. But there is not just that impulse between the colliding units. The string, it suddenly identifies that there is something going on, and there is force developed in the string for a short time, which is impulse of the tension produced in the string, right? So then let me get you past some very basic stuff here. Look, when this collision occurs, I want to be able to calculate the final velocities of everything here, assuming that small m, when it collides with this small m, it comes to rest. It sticks to this m. This m will stick to this m post collision. So let me assume that post collision, this is what happens. This is just before collision, and let's say just after collision, the following happens. Just after collision, let's say this is small m, this is small m, and this small little particle sticks to this m. So it's a perfectly inelastic collision. As you can see, it's a perfectly inelastic collision. Now, I want to calculate the velocities just after collision of this m and this m. Let's say this m and this m combo moves down with a velocity v post collision. Then because of a string consideration, this will move up with a velocity v, right? Now, let me write down the impulse equations for this particle, for this block, and for this block, right? Let's say this particle and this block, they exert impulses of magnitude j on each other, right? So now let me look at this point particle m. It's moving down with a velocity u, and when this hits this block, the block will exert on this particle an impulse j, and consequence to that impulse, consequently, this along with this particle along with this block, they move down with a velocity v. So now, what would be my impulse equation for this particle small m, right? Impulse in this direction is going to be final linear momentum in this direction. Linear momentum final is mv downwards. So in the direction of the impulse, it's minus mv minus initial linear momentum in this direction. Initial linear momentum is mu downwards. So in the upward direction is going to be minus mu. Yes or no? So that makes it like a mu minus mv. That's for the particle. That's for the particle, right? J. Now, for the block, look at this block. Let me call this block B. Let me call this block A. Now, for B, what happens? If B exerts on this particle a linear impulse J this way, this particle must be exerting on this block B a linear impulse J downwards. Yes or no? On this block B. Now, not just that. The block B has actually two impulses to be taken care of. It was originally at rest. There is the string that exerts a linear impulse because of the tension, which is Jt. There is an abrupt buildup of tension in the string, and there is a linear impulse because of tension in the string, call it Jt. Right? Impulse of tension. This is impulse of tension built up in the string. Now, impulse of tension means like I said, the impulse diagram for a particle or a system of particles can be just like you draw a regular free body diagram for forces. So then, this is the impulse diagram for the block B. There is an impulse J that this particle will exert on the block, and there is an upward impulse of tension because of the string Jd. Now, consequently, the net impulse acting on this and the final velocity of m is v downwards, right? So the net impulse downwards is j minus jt equals net downward impulse would be final downward linear momentum minus initial linear momentum, which was 0 for the block B. So that's equation 1. Equation 2, that is for the block B. Now for block A, realize that the block A has developed an upward velocity v. Why does that happen? That happens because there was an impulse of tension acting on block A because of the string jt. So it's jt which brings about a change in linear momentum of jt that brings about a change in linear momentum of of A. So that's going to be final linear momentum of A minus initial linear momentum of A. These are the three impulse equations that we have. Now I can plug into this equation jt. Jt therefore will turn out to be, jt is mv. This jt equal to mv, I plug into this, I get the value of j. Using 2 and 3, I get j. If I add these two equations, I get j equal to 2 mv. I get j equal to 2 mv. Now this j equal to 2 mv, I can plug into this. I can plug into equation 1. So if I plug j equal to 2 mv here, then 2 mv is mu minus mv, and that makes it u equal to v by 3. Or v, yes or no? I'm so sorry. V equal to u by 3. V equal to u by 3. Yes or no? That means the final velocity of the system is going to be 1/3 of u. And you know, this is how you write your impulse equations. Now you might be wondering, during this collision, there was also gravity acting on all of this. There was also gravity acting on all of this. And if there was gravity acting, would you not want to believe that there was an impulse associated with gravity? The impulse associated with gravity was mg into delta t. Now, so this also must have brought about a change in linear momentum, but I seem to have fooled you. What went wrong, or what was my assumption? Why have I ignored the impulse of gravity here? This mg into delta t was the additional change in linear momentum that should have been ideally accounted for in my linear equations that I have written, but nothing so far. Well, there is an approximation that we have taken care of. What we have assumed is that the force of collision is much larger than mg. So the impulse of mg compared to the impulse because of collision is extremely small, and therefore we discard ignore and reject the impact of mg in terms of producing an impulse. In general, when we also look at two particles colliding in mid-air, we conserve linear momentum. If there is no other external forces, we conserve linear momentum. Although there is gravity acting downwards, we end up conserving linear momentum for two particles colliding in mid-air only because that during that short period of collision, even though gravity acts, it is not able to bring about any perceptible significant change in linear momentum of the colliding entities, and therefore conservation of linear momentum becomes the order of the situation, and it's looked upon as sanguine, and we can very easily conserve linear momentum. So this in a certain sense was a brief outing with linear impulses. One of the things that you must understand is gravity in the context is referred to as a non-impulsive force, right? Whereas colliding forces are impulsive, certain forces don't contribute enough to change in linear momentum in that short a time because of their lower magnitudes. Those are non-impulsive forces. Spring forces are also looked upon as non-impulsive forces, right? So in the sense that, you know, if there is a mass m, there is a spring, there is another mass m prime, and there is a bullet of mass m double prime that collides with this mass m, and the spring is in its natural state, then between m prime and m I can conserve linear momentum, because the spring is unable to respond very quickly to this act and this action and this event, and therefore, you know, it's not able to contribute to change of linear momentum. So the springs are also looked upon as non-impulsive element. They take a little while to respond, they take a little while to act, and therefore, you know, the impulses that they could produce could be ignored or rejected. While we solve problems, we'll identify situations where, you know, the impulsive forces act, the non-impulsive forces act, and what to do with each one of them. But this much for this session. We'll solve a few problems on impulses after this. Thank you so much. Bye-bye.